This project is on secure machine learning in the cloud. And so I'm here on behalf of my colleagues, Roland Hostetler, who is the main investigator in the project, and Anders Oljen. We are at the Division of Signals and Systems in Uppsala University. So when do we need machine learning in the cloud? Well, obviously, there are many customers, say a hospital, which has a lot of data on patients, and they want to learn a model on a particular disease or how it progresses. However, they don't want to share the data directly. Or there could be more than one hospitals treating similar patients. They don't want to share the data with each other for privacy reasons. So how can we learn from this data? Because the hospitals don't have the computing power to implement a machine learning algorithm. So they want to use the cloud services, who are third parties and therefore not trusted. So one of the possible solutions is to use some kind of encryption. And whenever you use encryption, generally you need to be able to decrypt the data to be able to run the machine learning algorithms. And there comes homomorphic encryption, which has got various types of, various levels of encryption in it, that can allow you to essentially operate on the data or process the data, run algorithms or some kind of functions on the data while it is encrypted. So you don't need to decrypt it. You simply work on the encrypted data without knowing what's inside the data. So, so this is where machine learning in the cloud is obviously a service that many customers would like to avail of, and because it's convenient for them. But in order for them to trust this untrusted third party, they want to encrypt the data, and one of the possible solutions is this homomorphic encryption. So obviously, you can have issues with privacy. You can also have issues with data breaches and leaks and industrial or governmental espionage, etc. And there could be local legislation that prevent you from sharing the data, like GDPR, for example. So we have three main goals in the project. The first one is implementation of homomorphic encryption. So there's a picture on the right-hand side that shows that the top one is not homomorphic encryption. So where you want to work on the data, you have to decrypt the data and run your machine learning algorithm. That one at the bottom shows that you don't need to decrypt the data. You can actually run your algorithm on the encrypted data because of the homomorphic property of this encryption. The second objective is maintaining privacy of this data, and one of the very well-known and well-used notions of privacy, which originated from the database literature, is the differential privacy, where you can protect individual data in a data set. So if you change one element of this data set, and you have two data sets, one with the changed data and the other one the original one, and you make a query into this data set for, say, an average salary or something like that, then the output that you'll get from it, probabilistically, the probability of coming from either of these two data sets is very, very close. So therefore, you cannot tell that whether it came from the altered data set or it came from the original data set. So that's the notion of differential privacy, and essentially it's achieved by adding noise to the data. And the third goal is, of course, the very important goal of demonstration and implementation on a platform. And here we are working together with our partners in Intel and Swedom. So let's look at what homomorphic encryption does. So if you have a function that can essentially operate on some operation of x and y, which is the same as operating on the functions of f of x and f of y and then combining them. So in homomorphic encryption, that's what's happening. So basically, you can encrypt X and encrypt Y and do an operation, okay, say addition. That would be the same as adding X and Y and then encrypting it. So essentially, if you do encrypt X and encrypt Y and add them, so the person who is doing the addition doesn't know what the data X and Y are. They only see the encrypted version. When you add them, you get encrypted version of X plus Y, and then you decrypt it. The person who has the private key to decrypt can get X plus Y back from it. Okay? So the encrypt, you can use public keys, but to decrypt, you have to have access to the private key. So obviously, this sounds very, very exciting that you could do that, but what is the catch, right? So what would be the difficulty in doing this? So there are, the holy grail, if you like, is this so-called fully homomorphic encryption, which supports addition and multiplication, and computationally it's very complex. And generally, it's limited to integers, so any operations you do on numbers, if they're integers, it's easier. If they're real numbers or floating point numbers, then you will have some sort of approximation going on. Okay? And it's also how many consecutive operations you can do, say how many multiplications you can do on, in a consecutive way. That's also limited, and I'll explain that in a moment. And then there is this thing called partially homomorphic encryption, and there is another a name you'll sometimes find is somewhat homomorphic encryption. And here they support limited types of operations, so either addition or multiplication, not both, and computationally less complex, so they're easier to implement. But the problem is that you have to combine different schemes on some operations need to be done in plain text. So your security may be compromised in some cases. Okay, so the fully homomorphic encryption scheme that is the well-known scheme is the CKKS scheme. It was based on the names of the authors who published this paper. So it supports addition and multiplication, uses approximate arithmetic. It's leveled. What that means is that every time you do this encryption, you're adding some noise in some way to the number. Okay, so the more multiplications you do, the noise gets multiplied even more. Generally, it's known that addition doesn't increase the noise as much as multiplication does. So the number of multiplications, consecutive multiplications, is generally limited. So that's what we mean by levels. So how many multiplications you can do, that's usually limited. Okay? And complex functions can be implemented using polynomial approximations. An approximation must not exhaust the number of levels. Okay, so in order to prevent this noise from building up, because if the noise level goes up so high after consecutive multiplications or additions, then when you decrypt it, what you get back, it doesn't make sense, right? So you don't get back the original data. So some of the things that we have been trying to do within our computational limitations is these k nearest neighbors. It's a simplistic approach for classification, prediction, based on finding k closest points to a test input. Okay, so basically you find a cluster and you form these clusters, and eventually you get the test data, you compare it with these clusters and find which cluster it is closest to, and you say, it belongs to this cluster. So the computational primitives that you need, calculating the distance between data points, so Euclidean distance, comparing distances and sorting, a weighted average or majority vote, and things like that. So these are the operations you should be able to do. What we found is that individual multiplications may be computationally complex depending on the security parameters, but it's not a problem. We can handle it. Approximation of functions using polynomials consumes many levels due to the multiplications, and that's when the noise level can get very high when you try to decrypt the data. And good approximations often require high polynomial orders. Therefore, they consume many, many levels. And here comes a concept that was proposed by so-called bootstrapping, which was it refreshes the ciphertext from time to time. OK. So we have so far enhanced our understanding. We have done some design studies, and implementation of proof of concept is ongoing. And our partners are, it was a Vinnova-funded project with Swedom and Intel. Thank you.
Thank you very much.